So it's a great pleasure to have our own Kaushal Verma from ISC here, and he's going to talk about quadrature domains. So
yeah, thank you. So thank you very much. I'd like to begin by thanking Debraj, Sivaguru, and Diganta for the invitation to participate in this event. Very happy to be here, particularly to see the audience full. All right. So I thought I would try and convey some basic ideas of what quadrature domains are in this series of lectures. But before we sort of get into the definition and so forth, I'd like to begin by some motivation, to tell you what exactly the problem is. And as we move along in these series of lectures, I will then dwell upon some basic properties of these domains. And towards the end, I also hope to touch upon some aspects of this theory in higher dimensions. So that's roughly the plan for this series of lectures. So to start with, let's take a cubic polynomial. Just on the real line. And if you open any book on numerical integration or something like that, you will see a formula of this kind. That if you integrate this cubic from -1 to 1, you can actually get the answer just by evaluating this cubic at 3 points. This is p minus 1 plus 4/3 p of 0 plus 1/3 p of 1. And this is an exact formula. So the crux of this statement is that if you want to find the area under the curve of a cubic, it's enough to know the values at three points. And of course, you will notice that the coefficients, 1/3 and 4/3, these are uniform. They don't depend on the polynomial. So this is an example of a quadrature identity, exact quadrature identity. And formulae of this sort have been known for a very, very long time. Now, how do you prove such a thing? Well, a bare hands approach would be to just assume a certain form of a cubic, a general cubic, say ax cubed plus bx squared plus cx plus d, and just evaluate both sides and check that they are equal. Okay? But let's not adopt this ad hoc procedure. Let's try to sort of see some meaning in this equation here. So on the left hand side, you have the integral of this cubic, and I'm going to think of this as a linear functional on the space of degree 3 polynomials, at most 3. So the left hand side is linear as a function of p. On the right hand side, I have point evaluations at 3 distinct points, -1, 0, 1. Yeah? And this identity says that these two functionals, namely integration on the one hand, and on the other, a linear combination of point evaluations at 3 distinct points are the same. So with this viewpoint, you can try to understand what happens on a larger space, for example. So let's look at Pn, which is all polynomials of degree at most n. Okay. And let us restrict our attention on the interval 0 to 1, just for simplicity. So what I'm going to do is, I'm going to choose distinct points, say lambda 0, lambda 1, up to lambda n, distinct points in 0, 1, and I'm going to look at the evaluations at these distinct points. So let us give these some names. So L sub I of a polynomial P is going to be, by definition, I take this polynomial and evaluate it at the point lambda I. Yeah. So how many of these functionals do I have? I have exactly n plus 1, which is the dimension of this space also, Pn here. Okay. So now the claim is, or the observation, that this collection of linear functionals are linearly independent and a quick way to see this would be to assume that this is a linearly dependent set. So if not, then let's look at a certain combination, say alpha 0 L0, alpha 1 L1 plus alpha n Ln, and suppose this is the zero functional. What I do is I work with the canonical basis for this vector space, namely 1x, x squared up to x to the n, and I evaluate the left hand side on the set of all basis vectors, 1x, x squared, x to the n. So if I do that, we will get a system of equations, evaluate on the basis, and we will get equations of this form: alpha 0, alpha 1 plus alpha n equal to 0. This is what you get. You take the first constant polynomial, and then you get things like and so on. So this is
second equation you're evaluating.
exactly.
You're evaluating just the first power.
Yes.
Alpha 1 under 1.
Okay, so I have alpha 2, L2. Oh, right. Sorry. Absolutely. Thanks. Right. I'm all mixed up now. Absolutely. No, this is important. Yes. All right. So I'm going to think of this as a system of equations in the unknowns alpha i's. And if I look at the corresponding determinant of the coefficients, this is exactly the van der Monde determinant here. So the only solution is alpha I equal to 0, since by choice the lambdas are distinct here. Okay, so this is a linearly independent set, and now I'm going to think of integration as a functional, and this can be clearly represented as a linear combination of this collection of elements here. So this is the sum of, say, Cj, Lj. So this is the same as Cj P of lambda j. So this is the quadrature identity that we get if we adopt this linear algebra viewpoint here. Okay, now things like this are very useful because, you know, if you think about Simpson's rule for integration, it's exactly this. You see this identity can be scaled just by scaling the interval here, right? So if you have a function which is say C infinity smooth on an interval from A to B, you subdivide this into small pieces. On every piece, you can approximate your function by a cubic polynomial, and you have this exact identity there. And Simpson's rule will tell you that for a smooth function, the difference between the integral and this linear combination is an error which depends only on the fourth degree of the polynomial here. Okay, so that's exactly Simpson's rule. All right. Now, I was trying to understand the history of this subject for some now. And as I look back into the literature, a lot of work was done in the early 30s by people like Polyas. And this subject actually sort of took off in the late 60s when a mathematician named Philip Davis wrote a series of articles on this. So one of the goals that I want to achieve in this series of lectures is to follow Davis and tell you what really happened with his work. Right. So now the other question that arises is, well, of course we have this identity, but I would like to get a hold of these coefficients just for fun. What are these coefficients here? So that also can be done, and the way to do that would be to use the identify the CJs. So would be to use the Lagrange interpolation formula here. So I take a polynomial P of degree at most n, and I can write P as the sum of P of lambda I, 0 to n, and then I have the product of x minus lambda I divided by x minus lambda I. This is the index here. That's the entire product. And then I have the derivative of this product here. X minus lambda I. Right. Yeah, let me do this. Let me call this product as some A of x. So this is the same as the sum of P lambda I, A of x divided by x minus lambda I, A prime x, 0 to n. So this is always true. And then if you were to integrate both sides, then you can see what happens. You will get the sum of P lambda I, and then I have the integral of this factor here, x minus lambda I, A prime. Sorry. I have to evaluate this at x equals lambda I. So this is A prime at lambda I. 0 to 1. All right? So these are my coefficients here. And you can see that they don't depend on P at all. So independent of P. Okay. So let's, take this idea forward and ask the following questions. Well, let's fix our attention on the interval 0, 1. And you could consider various classes of functions now instead of polynomials. So maybe you could look at the class of all integrable functions, say. Integrable functions on 0, 1. And you could ask, is there a quadrature identity for this class of functions here? The answer is clearly no, because if you were to deal with only finitely many of these points lambda I, you could actually fool around with the function in between two of these points without changing the value at these points here, lambda i's. So the right hand side is not going to change, but the left hand side will change. So this simple observation tells you that if you were to have only finitely many points in such an identity, then there is no hope for something like this to be true for the class of integrable functions, because you can perturb the function. So maybe you could expand the scope of the definition and ask for something more. So suppose lambda i's are distinct points in 0, 1. We will say that a class of functions on 0, 1 admits a simple quadrature if the integral of f from 0 to 1 is the sum of Cj f of lambda j 0 to infinity, where Cj's are uniform in the sense that they don't depend on the function f, and f belongs to the class of functions, the given class of functions. Which one? I'm throwing in this infinite thing here. So here is another observation. If you recall our situation here, we looked at polynomials of degree at most n. Now let's allow unbounded degrees. Just look at all polynomials. All polynomials. Observation is, so observe, P admits a simple quadrature identity.
This doesn't get to argument about getting one's hands on these coefficients each day. But is the expression correct?
This one here?
I mean, it seems like since you have an x minus lambda I in the denominator, all that it's doing is it's clearing the relevant linear factor upstairs.
Yes.
So if you want to get P of lambda I to be equal to lambda I, what you simply want is the product of all but the ion factor.
Right.
The derivative gives you a superfluous constant.
Yes. So Gautam, what will happen is, suppose you want to capture P of lambda I on the left hand side. So
those things will also be.
Yeah, the other things will go away. The only surviving factor will cancel with A prime lambda I. Yeah. Okay, so here's an observation. If you look at all polynomials, no restriction on the degree, then this class admits a simple quadrature identity. Okay. What this is of course not unique. There are many ways to get these identities. Let me show you one way. So let's look at, so here's a sketch of a proof. You can find this in paper by Philip Davis. I forget the year, look it up. So, there's my book. Right. So let's choose. So let's choose an increasing sequence. So by the way, I'm no longer restricting to 0, 1 because I'm allowing all possible degrees here. I have to expand the domain here. So I'm looking at the entire real line. So I'm looking at the sequence which becomes unbounded, and I would like to create a quadrature identity using these points where the function is going to be evaluated. I'm going to integrate on 0, 1. Outside, exactly. Right. So if I have to create a quadrature identity for all polynomials, so I look at x to the n for some n. If I can express the integral of x to the n from 0 to 1 as a linear combination for all possible n, then I'm done. So that's the idea. So let's look at the integral of x to the n dx. This is 1 over n plus 1. And I would like to express this as a linear combination of point evaluations. This is lambda j to the n. Right? So this is evaluating x to the n at the point lambda j. That's what this is. Okay? And I would like this to be true for all n. So what do I have? I know what the lambda i's are. This is something that I have chosen. The unknowns are the CJs. So this is a system of equations, infinitely many equations in infinitely many unknowns. So there's a very nice theorem of Polyas around 1933 or so. So Polyas theorem says the following. So consider the following set of equations. Let's look at a00 x0 plus a01 x1 and so on equals b0. Let's look at a10 x0, a11 x1 equals b1 and so on. So let's look at this infinite system of equations and infinitely many unknowns. Okay, where's my danger mark? Is this acceptable? Is this visible, or shall I come back there? I'll come back here. Okay. Which one? Oh, infinity, yeah. Sorry. So let's look at that infinite set of equations. And here are two hypotheses. Suppose, number one, the limit as k tends to infinity of a j minus 1 comma k divided by a j comma k is 0 for every j. For every j. And this is a pointwise condition. There is no uniformity in j. I'm just saying that for every j, this limit must be 0. And secondly, let's look at the determinants of these minors in that infinite array there. So look at A0k, A0k plus n minus 1, a n minus 1k, a n minus 1k plus n minus 1. So think of the corresponding infinite matrix there, and you look at all possible minors of all possible sizes. This is not 0 for every n and k bigger than or equal to 0. So at every level, this is saying that that system of equations is non-singular at every level. And Polyas theorem says that there is a solution. There is a solution xi to that system of equations for which the series in the system of equations is absolutely convergent. Okay, so Polyas theorem tells us that under these two conditions, you do have a solution for this infinite array here. Okay, so let's try and appeal to this theorem here, keeping in mind that our system of equations has this form. So the column of scalar vectors is 1 over n plus 1. These are the bi's, and the the unknowns are the cj's. And then you have these known points, lambda j here. So these are the AIs. Okay, so let's continue. So in our situation, what are the AJKs? The AJKs are exactly lambda k j. And therefore, the limit as k goes to infinity of this ratio aj minus 1k, ajk. This is exactly the limit as k goes to infinity of 1 over lambda k, right? The powers cancel out. This goes to 0 simply because we've chosen the lambda i's to go up to infinity there. And each of these determinants is clearly non-vanishing because this is a van der Monde type determinant. All the points are distinct, so that's also non-vanishing. So there is a solution. And the moment you have a solution, you have created your simple quadrature identity for the class of all polynomials, where the evaluation happens at a sequence of points that goes up to infinity. Yeah, so there is nothing unique here. So there is a solution. Yes. Okay. So this is rather nice. All polynomials have a quadrature identity. Now, if you think about the Weierstrass approximation theorem, tells you that if you have a continuous function on a closed interval, you can approximate that by polynomials. So one would like to believe that if you have a certain property that holds for all polynomials, you could potentially pass to a limit and maybe get a quadrature identity for the class of continuous functions also. The answer is, doesn't hold true. So the class of continuous functions does not admit a simple quadrature. Yes, yes.
Outside, you can send the continuous function any way you want.
Yes.
Just make it zero.
Zero, absolutely.
No way.
There's no way. There's no way. So can check. the class of continuous functions does not admit a simple quadrature. Identity. Okay. No. So the theorem is that all polynomials admit a quadrature identity with evaluations at lambda I if and only if these lambda i's blow up to infinity. So that's a theorem. That's a theorem. Yeah. Okay. So much for motivation on the real line. And if you look at the works of Philip and his collaborators, there's some very interesting real analysis there. And they try their best to get quadrature formulas for more and more delicate classes of functions. So using this as motivation, let me now come to quadrature domains in the plane. I'm pretty sure that's true. I mean, you can look at lambda j is going to minus infinity and still get it. Yeah, I'm quite sure, I think. It needs to be checked. Still.
This is just a tool for proving one of the directions
Yes.
of that infinite here.
Yeah.
The going on to whichever infinity
Yes.
is just a way that you can go for your
That's correct. Yeah. So what we have shown is just one way of that theorem.
So the other direction should work.
And by the way, Polyas theorem is sort of very flexible. These are only two sufficient conditions that enable you to create these quadratures. If you read his 1933 paper, there are various other conditions, weaker conditions that he has imposed, under which you will still get this quadratures. See, ultimately, the point here is enabling this determinant to be non-zero is not such a big deal. All you have to do is choose your points to be distinct, and you get a van der Waals type thing. The crucial condition is this. Choosing powers is just one way of ensuring that this limit is zero. As you will realize, there's a lot of flexibility in choosing these. All you want is a certain ratio to go to zero. So hidden behind this philosophy is an entire class of quadratures. Right? So it's just a philosophy here. Okay, so let's come to quadrature domains in the plane now. Let's move from the real line to the complex plane. So we will say that domain omega in C is a quadrature domain. I'll write QD for short. For the class, I have to give you a class of functions, just like we considered polynomials, continuous functions, and so on. For the class of integrable holomorphic functions, so L1 script O, if the following condition is satisfied. Yeah. So here is my domain. If number one, there are finitely many points, say Q1 up to Qm in my domain omega, universal constants, what did I call my constants? AJKs, By universal I mean they don't depend on any element of L1 script O. Universal constants A, J, K such that what happens? Such that I have a quadrature identity in this sense. Such that. So I take any such that for any f in L1 script O of omega, the following identity holds. So I take one such f and I integrate this against standard Lebesgue measure on the domain omega. This must be equal to what do we want? What do we expect the definition to tell us? See, here in the case of the real line, we chose a bunch of points and we evaluated the function there, right? I'm trying to make the definition a little more general because I'm dealing with holomorphic functions. I can take the derivatives also. So I would like the right hand side be a linear combination of point evaluations at the QJs along with a specified number of finitely many derivatives at these points. That's all. So this is the sum. J goes from 1 up to m. The sum K goes from 0 up to Rj minus 1, Ajk. And I allow these many number of derivatives. K goes from Rj minus 1. And then I have the evaluation at Qj. This is true. So please note the points Qj's are fixed once and for all. The coefficients Ajk don't depend on f, and the number of derivatives is also fixed. Okay. So whenever I have a domain with this data, I will say that this is a quadrature domain for this class of functions. Now, you could of course change this class. You could look at L2 for example, as we'll do later on. L2 is much more richer. But just for the purposes of starting this discussion, this is a good enough class because the left hand side is well defined and this is nothing else but just evaluations here. Okay. Okay. And in the same spirit, you could replace the class of holomorphic functions by, say, harmonic functions and ask for the same sort of property to be true. You could also look at a certain class of subharmonic functions, say, for example, in which case demanding that something is equal for subharmonic functions is too rigid. You could replace this by a less than or equal to sign, for example. Right? So there are many, many variations, and I will try and say something about different classes also as we move along. But this is the sort of the best test class to work with. Okay. All right, so we have a definition, and the first thing to do is to look for examples. So the standard prototype example is that of the disk, for example. Yeah. So by the Cauchy integral formula, if I take omega to be the disk of radius r, and if I look at an integrable holomorphic function, then the integral of f on B0r dA, I think I should normalize by the area of the disk, which is pi r squared. I get the value at the center here, which is f of 0. Yeah. So I can reinterpret this in the following way. So the integral of f on my domain is a universal constant, which is pi r squared times evaluation at the center. So we have one example. Well, one is then tempted to make a following conjecture. Well, any simply connected domain which is not the entire complex plane is by the Riemann mapping theorem equivalent to the disk. And one would then like to say that every such simply connected domain is also a quadrature domain. As we will see, this is not true in general. And it will turn out that the class of quadrature domains is not preserved under conformal maps. So that's one thing, one moral that we will learn along the way here. Okay, apart from this very simple example, at the moment I cannot give you any other examples of quadrature domains. But it turns out that this is a very, very big class of domains. In fact, one of the theorems that we will prove later on is that you take any smoothly bounded domain in the plane, any domain, there is a quadrature domain which is sitting really, really close to it. As close as you want. Yeah? So this is in fact a collection which is dense in the class of smoothly bounded domains. Okay. Another very important property that we will encounter is that such domains have algebraic boundaries. It's quite a miracle that a condition like this encodes a lot of rigidity on the boundary itself. This is a theorem, a marvelous theorem in my opinion. We'll try to give at least two different proofs of this statement here. The quadrature domains have algebraic boundaries. And apart from that, we'll also see some non-examples. So I can tell you right now that even though the disk is a quadrature domain, if you were to distort the disk and make it an ellipse, that is not a quadrature domain. It becomes a quadrature domain in a very different sense, but not in this sense here. Okay. The annulus is also not a quadrature domain, an honest annulus. Yeah, two concentric circles. But by the density theorem, if you perturb this annulus just a little bit, there are lots of quadrature domains. So the interesting thing in this theory has been to understand the function theoretic and topological properties of this class of domains. That has been the effort. The effort has not been to evolve very esoteric modes of integration of function. That's not the point. The attempt has been to see what the consequences of this definition are at a function theoretic level. And we will also see some other consequences, namely, I just mentioned that the boundary has to be algebraic. So there's a polynomial whose zero set is the boundary, essentially. Can you say something about that polynomial? And it turns out that yes, you can nail down a lot of information about this polynomial. In fact, the leading term of this polynomial must be of the form x squared plus y squared to some power. You can say even that much. Okay? So, I mean, when I started learning these things, I was so delighted that a classical topic like this, in fact, has a lot of connection to several complex variables, which I will highlight in the coming few lectures. And I think this is, so I must also say that even though the theory in the complex plane is fairly well developed, a lot of things are known, the situation in higher dimensions is very poorly understood. It's just sort of beginning to take off at the moment. Okay, so let's begin by actually doing something. So there are various approaches to understanding this class of domains. So I will show both approaches. Let's start with the first one, studying what is called the Schwarz function. So anytime you have Schwarz on the blackboard or in the book, you can be sure that there is a reflection lurking just around the corner. So, and if you want a reflection to exist, your boundary should be real analytic to start with. So I will make the following assumption. So this is a local sort of analysis. So I have my domain omega with smooth real analytic boundary. All right. So here's the local situation. So here is the boundary of omega. This is 0. And let's assume that there's a local defining function which is rho equal to 0, which is real analytic and smooth. Okay. So assume that rho 0, 0. And d rho is not equal to 0. So I can write down a convergent power series for rho in the variables x and y. But I'll replace x and y by z and z bar, and I will get a power series in z, z bar. And because I'm assuming that the gradient is non-vanishing at the origin, there are going to be linear terms in this expansion here. And the moment you have linear terms, it's going to look like this. C10 z plus C01 bar z bar plus higher order terms. Right? And the other observation is that rho is a real valued function. So rho is equal to its conjugate, and therefore C10 is in fact the conjugate of C01 here, C01 bar. So if this is non-zero, this is also non-zero. Right? And therefore you can try to solve this equation for z bar in terms of z locally. So solve z bar in terms of z. Okay, so I take this to the left hand side, divide out by these coefficients, throw all the z stuff there. And if I'm careful enough with the bookkeeping, the right hand side will be a holomorphic function locally. So the defining function of the boundary can be rewritten in this form. Locally. And if you look at Schwarz's collected papers, this function makes its appearance there, and in the literature this is now called the Schwarz function associated to a smooth real analytic arc near a given point. Okay? So you can do this analysis near every boundary point here, and in each small open disk here like this, S is equal to Z bar. So therefore, if you were to look at the overlap of these two disks, you will have one definition for S and another definition for S, but they both are equal to Z bar, the common intersection. So by the identity theorem, this argument tells you that if you have such a domain, you can define this function S in sort of a tubular neighborhood of the boundary if there are no self-intersections. The moment you have self-intersections, S typically becomes multiple valued here. But if your domain omega is nice enough so that the boundary doesn't have self-intersections and so on, this is defined in an annular region around the boundary here. So well defined. So, so here's a proposition. Look at the function r, which is the conjugate of z. So this has a number of very interesting properties. So then r satisfies the following conditions. Maybe I'll write there. Then, number one, r of z is of course equal to z on the boundary of omega in some neighborhood u of 0. U is that disk that I drew there. This is clear because r is equal to z bar and z bar is equal to z. That's what it says. So suppose I call u plus minus as the two components of u. Yeah. Such? Yes, yes. That's because of the assumption that you have a convergent power series, and I'm assuming that the gradient is non-vanishing, so I have linear terms, and by the implicit function theorem, I'm solving for z bar in terms of z. Okay. So that's the idea. Secondly, so suppose we call these two components, the inner component and the outer component, as u plus, then r is in fact going to map the outside to the inside and vice versa. And finally, r is in fact an involution. So, just to summarize here, you have this neighborhood where S is defined and hence R is also defined. Property number one says that the boundary is in fact the fixed point set of R. The map R flips the outside and the inside, and this is an involution. So two flips get you back to where you started from. So this in fact is the reflection in a smooth real analytic arc. Okay. So I'll just summarize here. The way to construct this is you take your defining function, identify the Schwarz function, which is just the right hand side of z bar equal to this, and take its conjugate. That's your Schwarz reflection. Okay. Yes, yes, yeah. I'll show you some examples now. Yes, absolutely. So, some examples. It's exactly that, Debraj. There's nothing more. But you know, there is some advantage in stating this more generally, because even though we can locally straighten out real analytic arcs, we want to consider the entire domain all at once. That's the only thing. But I'll show you some examples. Yeah. By the way, was that a signal for me to stop? 5 more minutes. Yeah. Okay. Examples. I'll stop here. Let's take rho to be y. This is the function y. So, so rho equal to 0 is y equal to 0, which is the x-axis. And I will write this as z plus z bar equal to 0. So what is the Schwarz function here? Huh? Oh, z minus. So your Schwarz function is the identity here in this case. So what is R? R is z bar, and z bar is exactly the reflection in the x-axis. Let's look at the case of a circle. Let's take z minus a modulus squared equals r squared. So I can write z bar as a bar plus r over z minus a. Yeah? So solving z bar in terms of the other variables. So this is the Schwarz function right here. And r of z, which is the conjugate of s, is by definition a plus r squared over z bar minus a bar. And this everybody will recognize as the reflection in this given circle here. Right? That's your reflection. Yeah? And from school geometry, you will of course know that the product of the distances from the center, z minus a times z star minus a, is the square of the radius of the circle. So that's the inversion property which is encoded here. I'll give you one more example and then I'll stop. Let's take an ellipse. And let's assume that A is bigger than B. So again, write x in terms of z and z bar, y in terms of z and z bar, and solve for z bar in terms of z. Yeah? So if you do that, you will get the following expression. So I have a squared plus b squared, a squared minus b squared z, plus 2ab divided by b squared minus a squared. Then I have the square root of z squared minus a squared minus b squared. So that's my ellipse. I have the two foci here. So your Schwarz function is locally well defined, as we have seen. But if you complete the pilgrimage around two of these temple towns, so to speak, there is no phase change because you've gone around an even number of points here. That's why this is you can choose this without any ambiguity here. This is your Schwarz function. So three different kinds of behavior for the Schwarz function. This is very simple. This is an entire function. This has a pole, a simple pole, and this is multiple valued in the large. So let me stop here. And just to sort of summarize, just to sort of give you a preview, we will be continuing this approach tomorrow, and then quadrature domains will arise as those domains for which the Schwarz function has a certain characteristic property. So I will stop here.